Hey there everyone, welcome back to another video. So today's video is going to be quite a special and a long one because we are going to be looking at all the graphs in IGCSE Physics 0625 IGCSE. So without any further ado, let's get started. So first we have the graphs of motion. Let me choose a pen. Let's go with red, I guess. Okay. So as you can see, D stands for distance, okay? And T stands for time. So as as time increases, distance increases. So we can see here that the distance is rapidly increasing. In the second graph, we see that at first, initially, the graph increases very fast, but then eventually it starts to slow down. This one represents constant speed. So let me write that down. So constant speed. Okay, but over here you see that your distance is not changing. You're at one place, that's why your distance is not changing. So we call this no rest. Next, we come to speed time graph. So we have speed here or velocity. Oops, let me write this properly. Velocity, velocity and time. So over here, this kind of graph will be called increasing acceleration. So increasing acceleration, and this type of graph would be called a decreasing. Oops, wait, let me just quickly change this. Yes, so decreasing acceleration. Now it's acceleration because we see that as time increases, velocity increases, or speed changes as it increases, right? That's why change in speed as it increases is causing it to accelerate. Okay, so over here it's the acceleration is constantly increasing, but in this graph the acceleration is slowing down. Now over here, while this is increasing acceleration, this graph over here shows decreasing deceleration. So decreasing deceleration, whilst this graph here shows increasing deceleration. Deceler, just a second, deceleration. Okay. Then we have one more. So this graph here shows at rest because this is not a distance time graph. This is a speed time graph. So if my speed is 0, that means that I'm not moving, right? And if my speed is constant, that means that I'm moving at constant speed or constant velocity. Now those were graphs of motion. Then we need to look at so when we have a velocity time graph, right? And you're asked to find the distance, what you have to do is you have to find the area under the graph. That is the distance on a velocity time graph. Okay. Now when you're giving a shape like this, perhaps there are two ways that you can do. You can divide this like this. So it becomes a triangle here. Maybe you can divide it like this. So it becomes one triangle, two triangle, and the third one a rectangle. Or what you can also do is take this as a triangle and take the other part as a trapezium and then find the area. So there are multiple ways depending on the graph. Then we look at terminal velocity. Terminal velocity is when the upward force, so this upward force is equal to the downward force. Okay, so downward. Now if that is the case, that means that acceleration will be 0. So as something accelerates, so it's decreasing acceleration, so there comes a point where the acceleration becomes 0. Okay, so that is the time where it reaches terminal velocity. Now in many questions of physics, you'll have a parachute guy jumping from an airplane and all that. So after the parachute guy reaches terminal velocity, right? This is the point where he opens the not paragraph, oops, parachute. Is it E or without E? Okay, doesn't matter. So this is the place where the parachute opens, and then suddenly, the speed decreases, then again at this point the parachute, how do I even call him, the parachute guy, okay, reaches terminal velocity again, because upward force, as we said, equals to the downward force. So we are done with that. Let's go on to moment. Now, these are not typically the graphs that you, not the type of graphs or diagrams that you will see in IGCSE, but I'm just using them to explain the concept as well as just showing you the basics. Okay. So for moment, which is basically turning effect, let me write that down. Turning effect. This is what it basically is. So this is the clockwise movement, and this is the clockwise movement, and oops, I think this arrow should have been like this rather. So clockwise movement, and this is the anti-clockwise movement. Now when this clockwise moment is equal to the anti-clockwise moment, that is when this thing is in equilibrium. That's why it's stable like this. So that's with moment. Oops. Then we come on to momentum. Now momentum is basically mv, which is mass times velocity. And we have a particle. Velocity is vector, I think, which is why we can have velocity momentum to be positive or negative. So remember that if an object is going in this direction, its momentum is likely to be positive. But if that same object hits a wall like this and it bounces back, then its momentum becomes negative. That means that in a case like this, you instead of the typical equation is mv minus mu, right? So in a case like this, our equation might become mv plus mu. So you have to be careful with places like this, but when you practice MCQs and a few questions, you'll be fine with that. Then we move on to pressure in liquids. So this is the depth, and when we are asked to find the pressure in liquids, we use the formula P equal to dgh, where D stands for density, G stands for acceleration due to gravity, which is basically 9.8 the meters per second squared, I think. Yeah, and then depth is the height or depth, right? So also remember that we do have something called atmospheric pressure. Okay, so we have pressure in liquids, yes, but another pressure that is applied to these liquids is called atmospheric pressure. Yeah. So sometimes when you're doing MCQs, you have to be careful because you have to subtract the atmospheric pressure from the total pressure in order to get the pressure in liquids. So just be careful in places like this. Then we have molecule exerting pressure in a container. So we know that momentum is mass times velocity and impulse is force times time. So if you do, and impulse is also change in momentum. So if you do mv minus mu all over t, you get a force. Now because you have a container, this is the container wall, and you have particles constantly hitting and then going back, that means that they have mass, they are moving, which means they have velocity. So when they hit the surface at a particular time or in a given amount of time, they exert a force, which and you know that pressure is basically force over area. So we have a particle area at which at the point where the particle hits or the molecule hits, and we know it exerts a force. So force over area exerts pressure on the walls of the container. Okay, then we move on to wave. Okay, so as for waves, you need to know that these wave fronts are always going to be perpendicular like this, okay? And then the distance between this is called the wavelength, okay? If you don't know, this is the symbol for, this is lambda, which is the symbol for wavelength. So now when you're moving from deep water to shallow water, your ripples or your waterfront are going to move towards the normal. Okay, so initially, if this wasn't there, let's say this wasn't there, then it would have moved like this. But because that was there, it moved towards the normal. Now we know that the normal is always going to be 90 degrees or perpendicular to the surface. Now the surface is this time. So if this is the surface, then the normal will of course have to be like this. So if the wavefront has now tilted, that means that these ones are also going to twist. So that's why we do them like this. Now that is refraction, okay? We also have something called reflection of ripples or waves. Now, one thing about reflection that you need to know is that angle of incidence is always going to be angle of reflection. Okay, so when we have a surface over here, okay, or let's say a mirror, when a wave front or where ripples come like this, the angle of incidence formed over here, when it hits this and it goes in this way, is going to be the same angle over here. This shows us that reflection has taken place. Then we move on to diffraction. Now, you need to know some cases for diffraction, okay, some different situations. So the first one is that when you have wave how does it we okay, when you have it like this, right, the distance between them is lambda, as we know. So when it's moving through a barrier, it diffracts, okay? But if the gap of the barrier is bigger than this wavelength, then they will diffract in this manner, okay? So you need to know how they will diffract depending on the wavelength and the gap. uh then if the wavelength is bigger than the gap, then they'll diffract like this. And for this, okay, let me just number them. And for this one, if the gap is big, if no, if they are almost the same size, so this is lambda, then they diffract like this. Now, instead of having two barriers like this, which we do not have, if we only have one, then it will still turn a bit, but not that much, okay? So you could have this to be this big as well, and then this would become this, or different cases for here as well. But you don't need to know them all. Then we have the heating and cooling curve. This is not chemistry, so you don't need to know much details. So just need to know that at the beginning it's solid. Over here, this is the melting point. Okay, so this is where melting occurs. So solid turns into a liquid. Then it's liquid for all this temperature. Let me just remove this. Then over here, boiling takes place. So this becomes the boiling, just a second, boiling temperature or boiling point, okay? So and then it changes to a gas. Now know that this melting point and boiling point are only one are straight line, because at this points energy is being absorbed in order to break the bonds. That's why the temperature does not change. Then when you come to cooling curve, it's just the opposite. Now instead of us going up the stairs, we are coming down the stairs. Okay, so it's still going to be a gas, still a liquid, and still a solid. But instead of going up like this, we are coming down like this. So if that is so, then this means that here will be condensation and here would be freezing, right? So that's that. Then we move on to light. Now, so this is reflection. So now, as we said, so this is called the incident ray, this ray, and this is called the reflected ray because it's being reflected. Now, the same thing, angle of incidence is the same as same as angle of reflection. Now we need to know some few key scenarios over here. The first one we need to know, the first one that we're looking at is magnification. If the object is between the focal point and the center of the lens, then it will be magnified. How will it be magnified? So you draw your object, the top will come to the center and pass through the focal point, and the other will pass through the center. Now you will notice that these two rays will never meet. So if they will never meet, then we'll join these two back, and then it will form this magnified image. You can see that this is our original object and this is our image, which is way bigger in size, and it's further away from the center of the lens than the focal point. It's closer to the original object down to the lens, and other few characteristics. It's upright, enlarged, magnified, and blah blah blah. Then we go on to inverted image. Now, if this object is no longer between the focal point and the center of the lens, which means that it's no longer over here perhaps, and it's outside, that means that this time it will not be magnified. So you repeat the same process. The top goes to the center and then goes to the focal point. The other one goes to the center. But this time you will notice that these two meet at a point, and that is where you draw the other object. Now you'll notice that this image is actually an inverted image, right? Then once, okay, now let's assume that you have an object A, right? And this is a mirror, and maybe your eye is over here. So this is where you're looking at it from. So when you're looking at it from here, you do not see the object over here or here or here or here. You rather see it over here. Why? Because it's the same reflection laws, and so it's basically the two things we learned before. So let's say the point from here goes like this, and because it's a mirror, it's being reflected, it goes like this. So we are still following the same rule. Angle of reflection, angle of incidence is the same as angle of reflection. But this time, okay, so we'll come to that. Then maybe we have another point that goes like this, and then it gets reflected. So angle of incidence is still the same as angle of reflection. But now as you notice that these two rays, they never meet. That means that we draw them back. And the place where we draw them is where this object A's reflection is being able to see, with our eye being here. Note that our eye will never be here, here, or here. If our object is here, then we need to look at it from this side. Let me just clean that. Okay. Then we are almost there. So we also need to know the dispersion of light. Now, the light coming from here is a monochromatic light. Monochromatic light, which means light of a single frequency. So this is usually white light if we want to see the dispersion. So white light. So as it comes like this, it refracts, and then because they have different frequencies, they also diffract differently. So the one on top is red, followed by orange, yellow, green, blue, indigo, and then finally violet. Okay, so these diffract. So I haven't actually drawn the middle one, but they would have probably looked something like this and all, right? So that's dispersion of light. Note that there's a difference between diffraction, which is not the same as this. Then we come to electricity and magnetism. Now, if we know that a wire is going up like this, we need to know the direction of its magnetic field. If it's going up, then it will go in an anti-clockwise direction. But if it's rather going down, then it will go in a clockwise direction, the magnetic field. Okay, I think I'm not completely sure, but then this will be out of the paper, and this is into the paper. Now the way I remember it is that I imagine there's a table like this, and then there's a paper like this. Now if I'm going down, that means I'm going into the paper. If I'm bringing something out, that means it's out of the paper. So this is how I remember the into and out of the paper. Then we need to know the diode IV gram. So I actually stands, let me just write it properly. So I stands for current, and V stands for voltage. So this is how the IV diagram for a diode looks like, whereas the IV diagram for a filament looks like this. I'm not going to be covering the detail of why it looks like this because that will be a bit time consuming. Maybe I'll make separate videos on them if you put it in the comment. And then for an ohmic resistor, it's basically, a straight line. So those are the things that you need to know. Now, You see, when you're trying to find the force, the field, and the current, you often use Fleming's left-hand rule, right-hand rule. So when you're using it, right, your force is actually your thumb. The current is your middle finger, and then the field is the index finger, if I've named them correctly. So this is how you used to determine any one of them. Okay, yeah, okay, so any one of them, yes. Now this is so this is basically a coil of wires. Okay, so now this shows how the coil of wires tends. So you basically have to use the rules over here and apply them over here, because you see that you have a magnetic field. So you have a magnetic field which goes from north to south like this, and it's interacting with the magnetic field from here. So then not necessarily magnetic field. Yes, so the current's magnetic field how does it interact with it, which causes it to tend. Okay, I don't know if I've been able to explain this properly. This is one of the diagrams, okay? But I will make a separate video on this because I really want to explain unit 4 very well. So we need to know that, okay, if I didn't have this, okay, and I just had it like this, then when it's the current is going or flowing like this, right? This side will be north and this side will be south. If I want to draw its magnetic field, I know that it always goes from north to south. So not so then it goes north to south, right? So do this, I'll do this. So because it's going from north to south, so north to south and then north to south. Now this would eventually come back like this, so north to south, that's why I haven't drawn it. So we leave it like that. Then lastly, transformers. This is the transformers symbol when you're putting it on a on a diagram. But if you're asked to draw a transformer in a question, then this is how you draw it. Make sure that you have to label it. So you label it with iron core. This is your primary coil, and this is your secondary coil. And if they also tell you to tell the type of wires, you can say copper wires. Now, please be careful whether they say it's a step down transformer or a step up. That will depend, that question will then determine how many coils there are, how many coils you draw. Okay. Additionally, so with that, I also have added the symbols, which you can pause and take a screenshot or maybe read. Let me just decrease it. So there you go. Maybe take a screenshot, and with that, I'll also want you to take a screenshot of this, which I made, but I didn't use this to teach. And that's all that will be for this video. I hope you learned something new. Thank you for watching, and I'll see you in the next video. Till then, ta-da.